Morning, everyone. My name is Matt Herman. I'm with Bureau Happold out of the Chicago office. About 2 years ago, we were approached by Gensler to assist them in the design of a headquarter building for a bank out of Pittsburgh, Pennsylvania. The bank is PNC, and they wanted a new headquarters, and they wanted it to make a statement. So they had challenged the design team to come up with a number of innovative low-energy strategies. Gensler took the client team on a tour through Europe, in particular Germany, to look at a number of low-energy buildings that were already out there. And what came back from that trip was a desire stated by the client to pursue the option for natural ventilation. I was thinking about Jack Portman's speech earlier this week when he mentioned natural ventilation in China, and it made me think about Pittsburgh 30 years ago. If you know much about Pittsburgh, it was where a lot of steel and industry sat, and 30 years ago, the air was not nearly as clean as it is now. So there's been a transformation, and part of PNC's desire was to capitalize on that transformation and express it through the facade. The building massing itself is not necessarily radical. It's not a long, skinny building like you see sometimes in Germany. It's responding to some very real site constraints, as well as some height constraints, which are based to both program as well as cost. So you kind of see here that this evolution, this diagram was done by Gensler as they began to mass the building. And a couple of very simple and straightforward design decisions done during concept in collaboration with the engineering team allowed some opportunities to evolve as we moved into schematic design and into DD. One is reorientation of the south facade to true south, a little bit off the street grid, and that helped a lot in terms of solar access and orientation. Once the massing was laid out, we began to look at a whole series of sketches on how to move air, mass, and energy through the building. Although these were very crude, they became somewhat telling as the building began to evolve, and I think you can see there in the crown some of the initial ideas about potentially harvesting some of the heat there. Now, one thing to note about this building is that there are no photovoltaics and there are no wind turbines. Not because we're against them in any way, but the economic analysis that we did proved that in that utility market, it made more economic sense to purchase renewable power rather than put it on the building itself. But we still had this beautiful crown, which was an architectural statement, and we wanted to utilize it. And that led to a series of sketches where we began to think about the combination of wind and light, but not necessarily to generate electricity, which is about a third or fourth order conversion from the initial source of energy into electricity. Rather, we just wanted to convert it into heat and then utilize that heat in the summer and spring and fall to drive the stack effect and move the neutral pressure layer within the building up as high as possible. And then in the winter, perhaps utilize it as a preheat for incoming fresh air. So the combination of these two strategies within the architectural feature of the sloped roof kind of combined to create an opportunity that allow us to maximize the number of hours that we could potentially get natural ventilation. It's a pretty simple idea. The client liked the idea of being able to interact and influence the behavior of the staff in a way that allowed them to connect with the outside environment. And part of that is because the air is much cleaner today than it was 30 years ago. The other big driver was the idea of what it means to naturally ventilate a building. As engineers and architects think about it, we tend to think about air exchanges and CO2 levels, ASHRAE 62.1, ASHRAE standard 55, lots of different numbers. But the way a client experiences it is I open my window and fresh air comes in. Terms like fresh and not stale were being utilized. And we needed to come up with a language to discuss both with the client team as well as the architecture and engineering teams what it means to naturally ventilate a building. I think it's an interesting note that at the same time, the CTBUH was involved in generating the natural ventilation in tall buildings guideline. If you get a chance, it's a great document. We used it as for some of the case studies that are in there that are very valuable. In one of the drafts, it also mentioned that there's a lack of data and research that is out there on this particular topic in terms of hard numbers that you can go and get access to. There is CIBC's AM10, which is a great document. There's some fantastic formulas in there. But in general, part of the reason I'm here today is to change that and to start to disseminate some of the lessons learned on this project and others. One thing to notice, this is not a new idea. It's been done before. However, the configuration in North America in particular is unique, and we wanted to share. Which brings me to the 80-20 rule. In general, I'm sure you've found in your professional practice that you can get 80% there off common sense. It's that last 20% where risk sits. And I find that relationship kind of inversely proportional to energy savings. Over the last 10, 15 years as an industry, we've gotten pretty good at knowing how to reduce energy using good practice, best practice, to get about a 20% drop in reduction from, say, an ASHRAE 90.1 2004 building, using rules of thumb, existing equations. But that last 80% is not that easy to get. And one of the challenges put forward by the client was to push past that 20% LEED silver, LEED gold building into LEED platinum. To incorporate natural ventilation as one of the many low energy features, we utilized a series of technologies and tools, and this was supported by the use of the architectural and engineering team's application of BIM, taking some of those models and bringing them into analysis software. One thing to note about the analysis software, it was that it had to be able to incorporate the buoyancy calculations, pressure coefficients, and link that to dynamic simulation of both the mechanical system and the facade. In order to do that, you need to have an energy modeling tool that is dynamically linked to an airflow network. So two different physics engines linked together at each calculation time step. So for the architects in the room, this is probably a painful diagram to even look at. But what it represents is probably a fourth dimension of, or even a fifth or sixth dimension of building information modeling, where what you're seeing, these brown lines here, are control logic statements that then control various pieces of the mechanical system and also link back to the building geometry and, most importantly, the operation of the facade elements, the openings, as well as what eventually became the incorporation of a solar chimney. The other thing that we learned that was very important was to, although back of the envelope equations are incredibly useful, and the guidelines, including the CTBUH's guideline, has some great calculations in there, it is important to use a full dynamic simulation tool, because in the evaluation of the efficiency and control of the natural ventilation system, we really had to understand the hourly annual performance. That's 8,760 hours in a year simulated within the software in order to fully evaluate the opportunities of natural ventilation, as well as the risks. What came out of that process was another painful diagram. But within this diagram is the logic of the multivariable controls for both the facade and the mechanical system, which are a series of 3 tiers, starting at the double skin facade, linking time at each time step with the HVAC system, and then also to the solar chimney, which was located at the top of the roof. So this all came together. I'm going to roll through a series of diagrams to explain how the building is conceived. Construction is started. The diagrams on the left were done by Gensler to kind of explain the idea. There are 2 facades which wrap the building. They are double skin. And then sitting within the building is a series of shafts that link each floor plate to the solar chimney. I find it ironic that I'm presenting with fire engineers. One little bit of advice if you ever attempt this: do not approach a code official with the word solar chimney on your drawing set. Call it something else. It makes them nervous. As the heat from the chimney begins to create the draft that draws the air up, the facade opens up, and that allows that fresh feeling that the client expressed as desirable to be brought into the building. The buoyancy during a natural ventilation day is not that great. The delta T there between the inside and outside air temperature are not that high. And therefore, you're somewhat limited on the draw through the stack effect. And this is where the chimney and the solar collection comes into play, because we're trying to heat up that roof element and capture the solar access to get up to the 85 to 140 degree Fahrenheit range. 140 degrees is just the maximum that we capped out primarily to protect the seals of any of the glass elements. However, in some of we have a physical mock-up that's currently in Pittsburgh. We're seeing temperatures well above that. Series of louvers and dampers then regulate the airflow through the top of the chimney, which is also assisted by the airflow across the building. We saw, of course, as you'd expect, the maximum number of hours and draw during the spring and fall. However, there were a good number of hours during the summer when relative humidity levels were low enough to allow the facade to open up and to vent, even at night. And so there are extract fans which provide a boost should the solar chimney not have enough stack effect to draw the air out or achieve the sufficient number of air exchanges. This is a hybrid system, of course. There is a mechanical system. It is a dedicated outdoor air system with dual enthalpy heat recovery that then supplies active chilled beams. The active chilled beams are censored, dew point sensors, and have, again, a logic statement that link them to the operation of the facade, which includes incorporation and a fail-safe for any manual overrides that may occur. The active chilled beams represent a fairly significant fan energy reduction for us, and the use of natural ventilation augments that fan energy reduction even further. And we were seeing about a 75% reduction in the fan energy through the combination of these two technologies compared to an ASHRAE 90.1 baseline building 2007 version. I think 5–10 years ago, if you proposed an active chilled beam in the United States, a lot of people would look at you quite confused or crossed. That has changed dramatically in the last 10 years. And the technology is being incorporated from a lot of lessons learned in Europe quite rapidly across North America. We'd expect to see that occur in other regions of the world as well. The double skin facade gives us quite a few advantages. I think for those of you who have done the analysis on a double skin facade, you know that on energy alone, it doesn't have the payback to justify itself economically. However, in this case, it's doing about 3 or 4 things for us. Obviously, it's providing some energy savings through the increased U value of the assembly when it's in its closed configuration, but it's also slowing down the airspeed at the upper floors of the tower, where you tend to see elevated wind speeds. The idea here is to bring the air in slow and low and allow it to be drawn across the floor plate with sufficient air exchanges to pick up the heat from the occupants. The incorporation of a raised access floor, only 4 inches tall for power and data, along with the active chilled beam solution, allowed us to reduce the height of the overall building by about 3 to 4 floors, which equated to a fairly significant cost savings compared to the VAV baseline that we were carrying. So the combination of the active chilled beams plus the facade savings from the reduced height of the building actually gave us a positive payback before we even started. However, this again speaks to the integrated process. When we were doing the computational fluid dynamics modeling of the typical office floor plate, we modeled typical office furniture, working with Gensler's interiors team, who was doing the office innovation layout. We had set up an L-shaped desk. And what we realized was that the L-shaped desk of typical office furniture was creating a problem. It was causing the cool air that was being drawn in to pool within the first desk. Fairly obvious, fairly simple, but if you miss that detail and you're not coordinated, you're going to have problems and complaints. So again, some of the testing and integration of the design teams, both the curtain wall, the mechanical engineer, the controls vendor, and the architect and interiors was required in order to come up with design solutions. This one was fairly simple. Have the L of the desk that is running parallel to the facade have legs instead of a solid partition that dropped down to the ground. So making sure that that got into the specification was important. This is images from Gensler on the various facade configurations. You can see that unlike a lot of the double skin facades that you see in Germany, this one is utilizing a vertical pop-out window, the parallel pop-out windows, which changed the airflow within that cavity quite a bit. If you think about the horizontal openings, you've got maximum negative pressure down at the bottom of the cavity to draw air in, and then in the summer you want to vent that out at the top, utilizing the stack effect to create the flow. However, in a vertical configuration, the airflow is variable from top to bottom. It was just, again, another detail that had to be caught, and the use of computational fluid dynamics was a benefit in that particular case. We're making sure that we have enough free area within the pop-out windows to adequately vent the cavity so that it doesn't overheat in the summer. Now, the cavity is an important part of the overall building HVAC strategy because it houses the automated shades that reduce the solar load on the building to a point where the active chilled beam, the radiant component of the active chilled beam, can operate at its maximum efficiency. So here's just a quick diagram talking about the physics of that pop-out window where you get maximum flow down at the bottom, and as you move up towards the neutral pressure plane, the flow actually reduces, and then it picks back up in the exhaust as you move up towards the top. So that influenced our sizing calculations, where just using a rule of thumb calculation undersized the opening that we needed. We had to increase the opening slightly once this analysis was done and confirmed. Lots of different variables, and the use of Rhino and Grasshopper really helped out in terms of being able to iterate a number of different variables as we came and translated from the architecture into the analysis packages. Once we had enough of the variables set in terms of some of our sizing calculations, we then moved into doing a full building energy and CFD simulation. So here's where we're currently at. These drawings are, and analysis is still in process. We're in construction documents. We are under construction at the foundation. You can see here the neutral pressure plane. We've tried to move that up by generating heat in the chimney as high as possible. We're still trying to optimize this to get that neutral pressure layer up above the upper floor. However, these floors are envisioned currently as conference spaces and may not be optimal for natural ventilation due to acoustic purposes. However, the rest of the floors were able to get the pressure, the negative pressure through the return air shafts, draw the air in through the double skin facade. You can see here, this is the velocity increasing speed as we move up, and then ultimately exhausting out of the top of the solar ventilation cavity. And then checking that against temperature and comfort bands at each floor plate in order to ensure that comfort is maintained. And for this case, we decided not to use an overly expanded comfort band. We stuck within the ASHRAE 55 guidelines. However, the client is very interested in expanding that and capitalizing on the potential energy savings from an expanded comfort band for temperature. And there you can see the temperature banding. One thing to note here, there was a jog in the return air shaft in the core to accommodate this setback. And in the initial configuration, the jog was fairly subtle. We're now designing that out to eliminate the bit of heat gain that we're seeing here because of the turbulence created by the jog. I think you can probably see it in some of the other slides here. One other thing to note is that the building has to incorporate the facade pressure coefficients that were determined by the wind tunnel, and Boundary Layer was our wind tunnel consultant. So we also applied the data from their pressure taps into the CFD model to see what influence it had on the solar chimney and the stack effect. When all was said and done, we counted the number of hours that natural ventilation was in effect, utilizing this dynamic solution. The horizontal axis here is 365 days over a 24-hour cycle. This is noon. And you can see here, we ended up with over 2,000 hours of natural ventilation out of 8,760, which came to about 35% of the total number of hours. That accommodates both humidity and CO2 and temperature. And when this all came together, it resulted in about a 45 to 50% energy reduction and an energy use intensity of approximately 30 kBTU per square foot per year. So to conclude, we went from some early sketches to the image that you see on the left, which is a bit dated. It's changed a bit, but in general, we were able to achieve what we set out to with the client. We incorporated life safety factors, including fire and smoke, and ultimately want to share some of our experiences for not only the North American market, but for other areas of the world that natural ventilation may be appropriate. Thank you.